Okay, so maybe we should begin. It's a great pleasure to introduce Alexey Balitskiy from the University of Luxembourg. And he's going to talk about how packing simplices helps to study symplectic systoles. Thank you.
Thank you very much. Big thanks to Lucas, to Vinicius for inviting me here. On this last day of the conference, after the many caipirinhas yesterday, also on the day where there are just mostly short talks, I'm gonna perform in the genre which I call "This could have been a short talk." So it's gonna be very elementary. I hope you'll still find it fun. So we'll start with something, disappointingly elementary, perhaps. Here is my prototype problem. Some versions of this problem I will be, explaining to you throughout the hour. So you're given, let's start just from the plane. Usually Euclidean plane, you have several shapes, or let's say several triangles. You're allowed to translate them, but you cannot rotate them. And what you want to do, just for now think of this model example with just two triangles which are opposite to each other. What you want to do, you want to place them, you want to translate them, possibly with overlaps, so that they fit inside the convex shape of minimal area. Or in other words, you want to shift them around to minimize the area of the convex hull. So here, let's do a bunch of examples of this problem. And I want to go through a couple of examples and then explain, try to motivate why it's not that stupid as it looks. And then we'll do more examples. So it will be just a bunch of entertaining examples. So for this example, which I call example number 1, silly, you just notice, you just can play around, you can slide them around, and you see that, for example, those two arrangements are not minimal area of the convex hull. But there are actually many arrangements where the area is the same and it's minimal. So the most symmetric one is when you inscribe them inside the regular hexagon. But there are more, actually. So this hexagonal one is, in a sense, you can slide it around a little bit, more or less in any way, and the area will be constant. It's an exercise, high school exercise. And some critical position arrangements are the two pictures on the right. Here is a spoiler so that you get a little bit more motivated about this particular. So this particular hexagon, this particular problem with this particular answer being a hexagon is actually related to the theorem of Jeroen Straver, Vinicius Ramos, Daniel Sepe, which we learned about on Monday. It's related to the fact that the triangle multiplied by hexagon is a 4-dimensional symplectic ball. But for now, let's forget about this spoiler. Let's just discuss one unnecessarily complicated way to prove this obvious fact that, to minimize the area. So I'm going to pick a weird proof, which will generalize nicely to several more complicated examples. So the first step is having two triangles, which I can slide freely. Let's label their vertices in the way which I indicated in the picture. And let's connect those 6 vertices in that order by straight line segments so that we get a closed curve, this purple closed curve, which, it depends on the position of triangles. So I can slide triangles and I keep track of what's happening to the closed curve going through those vertices 1 through 6. We can compute its enclosed area of this closed curve. So how do I define it? Well, two obvious ways which are equivalent are, either you compute, this integral over the boundary. And in case when your closed curve just, walks around the convex region, for example, or if your closed curve is simple, doesn't have any intersections, self-intersections, then it's just the normal area. Or alternatively, you can label the regions in which your closed curve partitions the plane. You can label them with winding numbers. So for example, here in the middle, it's number +1, winding number +1, because the purple curve, you can like trace it. You can see it winds around once in the clockwise direction. -1 is counterclockwise. So apparently I chose not the most common convention, but whatever. So yeah, hopefully this makes sense, what enclosed area is. And it just happens, you check, you differentiate this area, you check what happens when you slide triangles, and it happens that it's constant. And then the second step would be to observe that the enclosed area oriented this area is less than the area of the convex hull of the 6 points. I don't know like an immediately obvious way to explain why this is true, but you can just slide them around and convince yourself that those winding numbers are in absolute value, they're at most 1. You can never get winding number 2. So in general, like this is not immediately obvious statement, because in general, you can imagine a closed curve which winds around the same region many, many times, and then the enclosed area will be the multiple of the area of the convex hull. So you have to say something. In this particular case, you can convince yourself it's true. In more general cases, you need some argument here, which I'm going to omit, because the example is silly. Yeah, but the conclusion then, if you adapt the two steps of this argument, the conclusion is that the area of the convex hull is minimal whenever our distinguished closed polygonal curve is in convex position. And for those examples, I just drew this curve, and you can see that here it's not in convex position, here it's not, but in the minimal examples it always is, so it's some kind of characterization. Okay, so if there are any questions about this silly example, please ask me.
This example, actually, so this proof seems to be to go through in smooth case, like in this way. Like
Yeah, more or less. Yeah. I'm only interested in the discrete case, in a sense, for the reasons that will be clear later. Yeah. Okay, so example number 2, not so silly. I give you the 4 shapes. These are 4 right triangles. The first one has 2 sides adjacent to the right angle, 1 and a greater than 1. The second one is just the minus first one. The third one is b and 1, b greater than 1. The fourth one is minus third one. So I'll explain where this example comes from, but for now, let's try to guess the answer. Okay, so it's not immediately obvious, and actually it took me, like 2 years and 2 collaborators to solve this particular example. So that's why it's not so silly. Yeah, we managed to prove this example, to find the answer for general A and B. And it happens, in this particular example, A and B are equal to 2. And you can see this picture. Yeah, you can convince yourself that all the 4 triangles are inside. So that's the answer. That's the area. And it's also the unique minimal example, unless your example belongs to certain one-dimensional family. And in that case, actually, you can deform this answer. So there is one-dimensional family of answers. I'm not drawing it. Okay, so I'm going to follow the same sketch of the proof and to convince you that the not-so-silly example can be proved along the same scheme, along the same lines. So consider the following closed polygonal curves. Here's the first one. I labeled the verses. I didn't draw the curve, but you have to follow like 1, 2, 3, 4, et cetera, et cetera. So it depends on the positions of triangles. Here's the second one, also not particularly obvious. Here's the third one, a bit simpler than the first 2. And then it just happens Yeah. So in the answer, if you draw the same curves in the answer, they just happen to follow the boundary of the answer. So yeah, that makes sense because we want, the enclosed area in a sense to be equal to the area of the convex hull, so it's natural to expect. And it happens that a certain linear combination of the three enclosed areas is constant. I cannot explain the meaning of these coefficients because this is not the only choice. Actually, there is I think, like a two-dimensional family of choices of coefficients for certain 4 polygonal curves. But for one of those choices, one of the coefficients is 0, and I chose it to just show it in one slide. But yeah, it might look like a complete mystery. I will explain where it comes from. But OK, the first step is then that certain linear combination of the enclosed areas is always constant. And then, yeah, you can compute this constant because we know, like for the optimal, hypothetically optimal example, we know how everything behaves. And then the second step would be prove the similar inequality that every enclosed area is actually less than the area of the convex hull. And here it's completely not obvious, and it's actually the same argument as before is just not true. So those, like even like for this first closed polygonal curve, you can slide triangles around the plane to make some winding numbers equal to 2. But if you do certain Steiner symmetrization-ish type of argument, you can modify the configuration to make the winding numbers less than 1 in absolute value. And the Steiner symmetrization will preserve the enclosed area and will decrease the area of the convex hull. So there is more, so there is some argument there. But basically, the sketch is the same as in the previous example. And that's how we get this answer. OK, now I want to explain first where those weird closed curves come from. Let's change the perspective. Let's draw our answer and think of it as a billiard table. So I drew the 2 triangles out of 4, the black ones, inside this billiard table. And I observed that I can interpolate between them by a family of closed curves with 4 edges each. So it just happens that all those curves are actually periodic billiard orbits inside this billiard table if your billiard dynamics is defined in a way which was presented by Pazit yesterday. So if your billiard reflection law is motivated by some kind of anisotropic physics laws, where you live in a normed plane with a certain, actually, it's not even like symmetric norm. It's some kind of whatever, like slight generalization, asymmetric norm space. Of which I drew the dual unit ball. So this is the polar body of the unit ball of my norm. So if then I try to write down the equations of the billiard dynamics so that the ray of light chooses shortest path, et cetera, then first of all, I know how to measure lengths. And second of all, I know how to reflect in the sides. So I'll give you a very brief, I'll just go through this very quickly because Pazit already explained this. So if you have an initial position of your billiard ball and you have an initial momentum on the boundary of the dual unit ball, the first thing you do, you draw the outer normal, which is your initial velocity. You follow this velocity until you hit the boundary. That's like how I get my first hit. Then I need to define the reflection. For this, I draw the inner normal at the point of the first hit for the billiard table. I follow this inner normal in the dual picture until I hit the boundary of the dual unit ball. That's how I get the new velocity. I follow the new velocity to find the second hit, et cetera, et cetera, et cetera, et cetera. and so on and so forth, until it just happens that in this particular example, it closes up for some miraculous reason. So yeah, trust me, I started with a more or less random point inside the more or less random momentum, and it happened to close up. So this phenomenon also has to do with many of the symplectic things that we heard about during this conference. I'll mention them very briefly because I intentionally want to keep my talk elementary without going in too much to the symplectic side. The main reason being that I'm not an expert in symplectic side whatsoever. All right, so using this dynamics, we can define a notion of a periodic billiard orbit in the sphere kt, where k is my billiard table, and t is the polar body, the dual body for the unit ball of my norm. It's known, it's due to Shirach-Steiner-Vidana neurons reverse, that basically you can view the same picture as inside the product of k times t on the boundary of the product k times t embedded in the four-dimensional real vector space or equivalently two-dimensional complex space. And this curve corresponding to the billiard orbit on the boundary will correspond to the, as long as your billiard orbit is periodic, it will correspond to closed Reb orbit on the boundary, where closed Reb orbit was defined way too many times, but I still wrote some definition. So, you know, like in most points, the direction you follow is just rotation with the your complex I of the outer normal for your body. You have to explain what happens properly when this point x of t lies on a non-smooth point of the part of the boundary, but it's doable, and yeah, and we've already seen this. And it happens that the symplectic action of the Reb orbit is the same as the length of the billiard orbit measured in this weird norm, which I here denoted with norm sub t, but I guess I should have done it. Yeah, sorry, it should be t dual, like t with a little circle, like here. Yeah, so if you want to forget about the symplectic side, feel free to do so. For now, it's only important that all those objects also show up in a very related symplectic picture. And I can define the systole of my pair kt as the shortest length of a periodic billiard orbit. It's known that it exists, shortest periodic billiard orbit. And yeah, equivalently, you can also define it in symplectic terms, and it's also known as the Eckland-Hofer capacity of the Lagrangian product k times t, which is important for the motivation, but absolutely unimportant for the problems that I'm explaining in this talk. So systole was the shortest length of a periodic billiard orbit, but in this particular peculiar example, it just happens that you can foliate your k and t in a very nice ways. It just happens that no matter where you start, in which direction you shoot your billiard ball, it will just close up always, almost always. So it just happens that in this particular case, you can foliate the boundary of k times t with very nice closed orbits. I mean, I'm exaggerate a little bit, but not too much. And so yeah, I just wanted to say the word diastolic because the conference is called diastolic, but it didn't really sound much. Here, yeah. So diastole is an informal umbrella term for many things, which is some kind of like min-max when you foliate your manifold or whatever with lower dimensional objects, and then you pick the largest one and you measure the size of the largest object, and then you minimize over all sweep outs or foliations or slicings or whatever. So you can define a diastolic type of thing. But I only defined it to include the word diastole in this talk, but it's not really important. The important part that this peculiar behavior is, like in this case, you have that the systole is equal to the diastole.
The action is a fixed event, right?
Sorry, what's that?
The action is
Yes, 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 yes. Yeah, so in this particular example, the boundary of the product is foliated nicely by periodic billiard orbits of minimal length, which has to do what other people call toll, but it's not exactly it. It's a weaker notion, and yeah. And until very recently, we didn't even have, I guess, a definition of what it means to be toll for non-smooth bodies inside R2N. I guess now we have such a definition due to Stefan Maciejewicz. Sorry, say it again. Yeah. But yeah, you can prove that the shortest one, like you can prove separately that the shortest one is this one, and yeah. Let's go to the. Then you can take it to plus infinity, yes. But again, this notion is really unimportant. I just wanted to say that. I would use the word diastole to say, in other words, that in this particular example, the billiard dynamics is, particularly nice. Okay, so here is some pictures which, like roughly correspond to the fact that you can foliate your billiard configuration with periodic billiard orbits of the same length. So I drew those billiard trajectories. I didn't draw what happens in the dual unit ball. It's, in a sense, it's unimportant for this argument. But let's just look at these pictures. So here, between the two triangles, I interpolated with one family of periodic billiard orbits, all of them having the same length. Then I interpolated between two other triangles and interpolated between another pair of triangles. And if I draw all these three things in the same picture, I only leave, like in this picture, I only leave parts of the trajectories parallel to the certain direction. And then you just notice that you can draw them nicely in the same billiard table. And then if you just label all the important nodes along the boundary in this particular foliation, you recover the third closed curve that was part of the proof. And similarly, you can find other closed curves. And that's how you find them, so the original proof, which might have seemed like unmotivated, it actually comes from a closer look at the billiard dynamics. All right, so I'm not gonna refer to symplectic capacities more or less, apart from the, like this characterization of Arstein-Evdan and Ostrover, saying that the symplectic capacity, or we can just refer to the shortest billiard orbit, closed billiard orbit. So capacity is at least one if and only if all your periodic billiard orbits in your configuration have length at least one. As I said, it's a theorem that they always exist, closed billiard orbits, so it's equivalent thing. Then there is like this question, at least for TB in Euclidean ball, so for like normal billiard orbits, normal Euclidean billiard orbits with the usual reflection, like angle of incidence and reflection are the same. Like in that particular case, this problem has been studied before. And I found the roots of this equivalence in the paper from the late 80s of Karay Bezdek and Robert Connolly, where they explain, in the case of TB in just the usual ball, that it's equivalent to say, like if you want to write the characterization, what it means that all periodic billiard orbits have length at this one, it's the same thing to say that all closed curves of length 1 can be covered by a translate of your billiard table. So there are many other names which I should have written here, but yeah. I was able to track down the ideas of this argument back to the late 80s. And then there is a statement which is, in a sense, is like the main statement of this talk, which is instead of considering all, there is another reduction to make this problem much, simpler, much approachable approachable by a computer algorithm, like finite in a sense. So instead of looking at all closed curves of length 1, you can only look at certain distinguished curves which will have length 1. They all will be just like triangles, and they will be determined in a specific way, which I will explain, by your dual unit ball T. And then you have finitely many shapes. You check that all those finitely many shapes can be covered by a translate of K. And then you know that the capacity is at least 1. So like the original notion of symplectic capacity, which is notoriously hard to compute, in this particular case can be reduced to something very elementary. So I wrote folklore because I guess like this statement was kind of obvious to posit as well in your own, I guess. I don't know. But yeah, I mean, whatever. I would like to attribute it to myself, but apparently it was obvious to experts in the area. Just to say that, like what kind of flavor of the statement. So if you want that the top statement implies the bottom one is obvious, because all those triangles will be curves of length 1. But if you want to prove it in the other direction, you need to prove some statement of this flavor. So this is just one example. So if you know that those two triangles can be covered by a translate of your, like each of them can be independently covered by a translate of K, then more complicated curves of also length 1, normed length 1, which follow the same directions more or less, can be also covered by a translate of K. And a priori, this is not obvious because, for example, this particular trajectory cannot be covered by either of the two triangles. But it can be covered by a convex set which covers both triangles. So there is some argument here to write down, which, some classical convexity style of argument. All right, so now I'm going to formulate what's this set of distinguished triangles. Explicitly. You have a given convex polygon, which is the unit body, the dual unit bodies of the norm. You can forget about the norm geometry from now on because I'm just going to explain very explicitly how you draw these triangles, which you want to translate to minimize their convex hull. You do the following thing. For every triple of outer normals that have a positive linear dependence, like in this example, so like there is a positive linear combination equal to 0 of them. I should say every, yeah, okay, for now, let's just say the triple of outer normals positive linear dependence. Let's draw the unique triangle following these vectors in the same order. And I want the perimeter of this triangle to have the T length 1. Do this over all triples of normals. I said triples, but in fact, you consider minimal sets of outer normal vectors which admit a positive linear dependence. So if you have two parallel sides of your polygon, you also consider just a pair, and you instead of a triangle, you just draw a straight line segment of so that double. When you traverse it twice, it's length 1. And then the bottom line of everything that I was saying before is that capacity is at least 1 if and only if each of those triangles can be covered by a translate of K. And you can see that in this particular example, from this dual unit ball, I recover the 4 triangles from my example number 2. All right, conjecture. The area that you need is at least 1 over twice the area of T. Where does it come from? Well, OK, so in the 2 examples before, this conjecture was true. So it's true for T equal triangle, which we'll get back to, but it's exactly the statement of the first example. And it's also true for any quadrilateral, which after some affine change, you can always reduce to this case, which was considered in the example number 2. And this conjecture holds. And in both cases, this is optimal. You cannot prove a stronger inequality because there are equality cases. Everything that I was saying, not specific to the plane, you can formulate the same question in Rn. Having any convex polytope, you draw all the distinguished simplices in the following way. You pick any minimal set of outer normals for the facets of your polytope with positive linear dependence. You draw all, for every order of those normals, you draw a corresponding closed polygonal line. And it happens to be a simplex of dimension between 1 and n. So it could be a straight line segment, could be a triangle, could be a full dimensional simplex. You draw all of them. You try to minimize the volume of the convex hull. And the conjecture is this now. Or using the symplectic reformulation. It's the same as to say, if your capacity of the billiard pair KT is at least 1, then the volume of K times volume of T is at least something. So in this form, it's famous as the Villeroy-Boas conjecture. Actually, it's a very special case, only for Lagrangian products, only for a specific capacity, but whatever. But it is already very interesting in this case because it implies a very widely open, long-standing conjecture of Mahler. And yeah, we heard this before, this reduction before already. So this is just to say that this problem, even if it looks simple, it cannot be simple because it implies Mahler. And we only know Mahler's conjecture in dimension 3 and below. Okay, why would anyone care? Okay. Because it's fun, because it implies Mahler's conjecture, because it allows you to prove special cases of Villeroy-Boas conjecture. So for example, this example number 2 basically implies immediately, what immediately follows from it, that Villeroy-Boas conjecture holds for all Lagrangian products of any quadrilateral times any convex shape. And we can also write down the characterization of the equality cases. And also, figuring out equality cases in Villeroy-Boas conjecture also is always interesting because they are often cool, and symplectic people sometimes like them because they tend to exhibit some other peculiar symplectic properties, such as tall-ish style property when the systole is equal to the diastole. Or, like in much greater generality, they happen to be symplectomorphic to a ball. Or there are other things, like you should ask symplectic people. They'll tell you about subadditivity, problem for capacities. Maybe they'll tell you about, some capacities coinciding. So there are many hypothetical manifestations of this, ball-like properties in symplectic world. Having said that, let's go through, with this motivation, let's go through more examples. Example number 3, which I asked to do 2 undergrad students in Luxembourg. So what I asked them to do, I just gave them, I explained the problem. You start with this pentagon. Actually, they did it for some deformations of this pentagon as well. But for this particular pentagon T, you draw the simplices in the way that I explained. So you pick, for example, you can pick a triple of normals, 1, 2, 3, like here. You draw the unique triangle following of the given perimeter, following those vectors, directions. But you will also have straight line segments because, for example, you have pairs of parallel faces, parallel sides. So for them, you have distinguished straight line segments. So now I have those 4 guys. I asked Thomas and Lou to minimize the try to experimentally, like numerically with computer, minimize the area of the convex hull. Here's the answer that they found. And it happens that, yeah, it holds with a little bit, you know, it's the equality, the robust equality is not attained. So the conjecture holds with a little bit of a margin, like 2% or something, I don't remember. And also in all the variations, deformations of this example, the verbal conjecture was true. But then something that we already heard about. So the example number 4 is what happens when your T is regular pentagon. In this case, you have 5 ways to pick a triple of normals, 2 ways to order them. In total, you have 10 different triangles, but they all look like this. So this is one of them, but there are also 9 rotated copies of it. And then you try to minimize the area of the convex hull, and what you get is the famous counterexample of Pasit and Euron. So it happens to be a regular pentagon. You can convince yourself that you, like, I drew this one. You can also flip it with respect to the vertical side, so that you get another one, and all the 5 rotations of the same picture also fit inside. And it happens that in this area, the conjecture is not true. And yeah, it's not true even like, you know, like it's 4% over the original conjectured value. Are there any questions maybe so far? Okay, more examples. You take regular hexagon, you do the procedure that I described, you have 5 shapes to fit in the polygon of the smallest area. Here's one answer, which is not surprising given the fact that we know that the configuration of triangle and hexagon is a symplectic ball. So it has to have all those type of properties, which are much weaker than being a symplectic ball, apparently. Yeah, what I didn't say that, you know, this billiar configuration was actually very symmetric. You can change the billiard table with the dual unit ball, and it will be pretty much the same picture. So, yeah. This problem is formulated in a non-symmetric way. Here, the shape T and the answer, you know, they play a very asymmetric role in the formulation. But it's equivalent to a problem which is symmetric with respect to swapping them. But OK, why I'm putting it here, because this is not the only equality case. This is one of them. But there are actually disconnected two-dimensional family of other cases. And also you can consider minus all of these, and you get actually 4 connected components. And we can prove that this is all, but I guess the general structure looks kind of confusing. And it would be interesting to understand if you can multiply this T by this not symmetric hexagon, and it's unclear if it's a ball or not. But maybe it's symplectically a ball. Yeah, the corollary in terms of the verbose conjecture, not particularly exciting, perhaps. OK, so one more example, which I included after Euron asked me, you know, like, so it's not exactly an example in the same fashion, because your T is not a polygon here. It's a smooth, round circle. But you can do the same problem, except like there is no finite algorithm now to do. But what you do here, like you're starting from any, you start from any triple of normals or any pair of opposite vectors, and you draw basically all triangles of perimeter 1 in the usual Euclidean norm. And you also include the degenerate triangles, which are straight line segments of length 1/2. It seemed like this problem was famous, and this was actually the motivation for Besdick and Connolly to write their paper, where they explained the characterization of, you know, like shortest billiards in terms of this type of convex packing problems. So it's an old problem from the 70s. Find the convex shape of smallest area whose translate can cover any closed curve of length 1. And it thanks to the result of Balitskiy and Connolly, it's equivalent to a question which I can formulate in symplectic terms by saying that, yeah, let's maximize this systolic ratio. Or you can also view it as an iso-mean billiard problem, meaning that if you consider all shapes with the same length of a shortest closed billiard trajectory, Euclidean normal, then you want to find the smallest area of such a shape. So we don't know the answer. Wetzel gives some bounds, Balitskiy only gives some bounds, and I think with Arsenia Kapyan we found a better example than any of them. I briefly explained this example. So I drew a parabola with the focus at that red point, so that every ray of light passing through this focus reflects and goes horizontally to the right. I mark a little segment on this parabola. I reflect it like this. So now if I do reflections of light, any ray passing through the focus will reflect twice and go through the focus again. And now I repeat this picture with, like I just do some kind of D3, the hydral 3 symmetry to draw 6 little parabolas. And this is our conjectured optimal example. So we know that we checked with Arsenia that every closed curve of length 1 fits inside. We checked that its area is smaller than all the previously known examples. We don't know how to prove it's optimal. But you can see some of the triangles of, like billiard triangles of perimeter 1 here. So it looks somewhat convincing. And it's not written down anywhere, so this is the only place. OK, I want to spend last 15 minutes on discussing a completely different method of proving results of the same fashion. You have a bunch of convex shapes. You want to minimize the area of the convex hull. And for this, I want to go back to the first example, the silly example, which corresponds to TB in a triangle. And I want to give another proof of it, which will be also unnecessarily long, but enlightening. Reformulation of the problem. Prove that lower bound for the area for any convex shape that can be translated to cover each of those two triangles. And potentially characterize equality cases. Would be nice because we know it just happens that Virubos equality is attained, so those equality cases are also interesting. They're potentially symplectic balls. Here's another proof, which I like very much. And yeah, I came up with it like forever ago. It's published. Notice that those triangles can be used to tile the plane nicely. Let's denote lambda the lattice of the nodes. Yeah. So one observation that this tiling happens to be just a bunch of lines intersecting nicely. So it's somewhat important for the sequel. It's enough if I want to prove a lower bound for the area of my shape, which covers those two triangles, right? It's enough to prove that if I translate my convex shape shifted by every lattice vector and consider the union, that I could cover the whole plane. If I do this, then I know that the area of my original shape is at least the area of any fundamental domain of my lattice. So it's enough to prove this. Let's assume it's not true. Let's assume that it doesn't cover the whole plane. So then, K doesn't cover. You can then, by shifting this picture, shifting K a little bit, you can assume that just K doesn't intersect lambda whatsoever. Because if this translated union was not covered in some point, let's shift it so that it becomes the origin, and then because of the translation symmetry, K doesn't cover any other lattice point. So okay, then I can draw my K in this picture so that it doesn't touch any of the nodes of the lattice. Now I draw at each lattice point, I draw a vector which points away from my convex shape K. And I extend it so that it becomes a vector field defined or on the entire plane. Extend finally on each simplex, on each triangle. Then, by some kind of like very simple topology argument equivalent to Brouwer's fixed point theorem, it follows that there is actually a point where this vector field has to vanish. Why? Because if you look how this vector fields look very, very, very far away from K, it just always points outside. So it's kind of like degree 1. Yeah. So it has to have a 0 somewhere, a continuous vector field. Assume that this solid black triangle is the one which covers my point X where the vector field vanishes. What does it mean? It means that the three vectors, the three orange vectors at the vertices of these triangles, they kind of point in different directions. Some positive linear combination of them is 0. And it can be shown in its simple lemma, which also was written in those old papers by Bezdek and maybe even Wetzel, I'm not sure. So it follows that this K is kind of, it's like more or less sits inside this cage. You cannot actually cover this particular triangle by a translate of K because K is some kind of, in a sense, it's caged by the vertices of this triangle. So it's also like elementary convexity argument. All right, so we proved some lower bound for the area. Next question, why is it optimal? So I drew the most symmetric fundamental domain here, which is the hexagon in this particular case. Why is this optimal? Well, in order to check it's optimal, let's just check that this particular most symmetric domain, K, which is the regular hexagon, that it works. It satisfies the condition that you can cover both triangles. Yes, you check it directly, it's obvious, it covers. All right, so we have the sharp inequality. And then the next question, which actually was not a part of the paper where I published this, can we characterize the equality cases? Because back then I could not do this. I mean, in the plane, of course, it's obvious how to do this. But what I'm going to say in a minute is a higher dimensional generalization of this. So, but from this argument, it seems, it is more or less clear that equality cases can only happen when K is a convex fundamental domain. So the translations of K cover the entire plane without overlaps. But it's not just any convex fundamental domain. It's also a domain which can cover two triangles. So from these two conditions, without going into details, I'm just going to write down one confusing way of characterizing these shapes. So K is more or less the same, in a certain sense, is the Voronoi cell, I'll explain what it means in a second, of my lattice lambda with respect to a quadratic distance form, which is written down here. So let's first take a look at this quadratic form. So I have arbitrary positive numbers Wi here. And the sum is taken, like there are three summands which correspond to three lines passing through the origin in this picture. So di are normal vectors to those three lines. And then I can just write down this positive quadratic form. There is three-dimensional family of forms, but two-dimensional family of Voronoi cells. What is a Voronoi cell? So given a distance, way of measuring distance, I can consider the set of all points in the plane which are closer with respect to this distance to the origin than to any other plane of lambda. This is one particular example of this potential Voronoi cell. It's also a hexagon, but it's deformed in some way. And it just happens that for all those quadratic forms, another different way to characterize those things is to say that these are exactly the quadratic distance forms for which my tiling is the Delaunay tiling, which I can explain if you ask me in person, if you're interested in some kind of discrete geometry. But it's just another way of characterizing the same entities. And actually, I didn't write it down, but I should have done this. It's the fact that only those quadratic forms correspond to Delaunay tilings like this is due to Erdal. It's like from late 90s or something like that. And also I have this approximate equal because there are actually some degenerate cases when you, for example, you send sum of w's to 0 with different speed, then it can degenerate and it will also be an answer. But yeah, but so basically the answer is just all limits of things like this is all the equality cases. Yeah. So this is just yet another way of characterizing something which I did during the first 5 minutes of my talk, which was, I was drawing some polygonal lines, and I was saying that equality is attained if and only if it's in convex position. So this is another characterization of the same, which has the virtue of that you can generalize it to dimension n. So this is more or less the only n-dimensional problem which I can solve, I believe, completely. Now T is a regular n simplex. For every ordering of facets, ordering of outer normals, you can draw a closed curve which spans a simplex. There are n factorial of them, cyclic orderings of n+1 vectors. And a formulation of my prototype problem is that I'm looking for a lower bound for the volume of a convex body, which can be translated to cover each of the n factorial distinguished simplices. So computationally, it doesn't look good because of the factorial. But in this particular case, the bottom line is that the same argument works. So first of all, I can repeat the first step, which is it just happens that all those n factorial simplices tile the n-dimensional space nicely. Moreover, this tiling is a dicing, it's so-called dicing, which means that it's formed by several families of parallel hyperplanes. It's a very specific subclass of tilings. And the nodes of this dicing is the famous AN star lattice. It's dual to the root lattice AN, or some people would call it the weight lattice of type AN. Okay, whatever. Yeah, I just wrote it down. It's inside, you can think of it lying inside the n-dimensional plane with sum of coordinates being 0 in dimension n+1s, but it essentially lives in an n-dimensional space. And the step number 2 goes without any changes, goes through nicely, and you can prove that since K can cover every simplex of this tiling, its volume is bigger than the volume of any fundamental domain. And then in particular, I can choose my favorite fundamental domain. My favorite fundamental domain is the most symmetric one. It's the Voronoi cell of AN star with respect to the usual Euclidean norm. It's called promotahedron. Yeah, there are more famous ways to define this object, such as it's the convex hull of all vectors which are obtained by permuting numbers 1 through n. Something like that. But, that's an equivalent definition. And then the next question, okay, we proved some inequality. Why is it optimal? Because you can check in a straightforward way that this promotahedron actually contains copies, translated copies of all of the distinguished simplices. And my original argument why it was optimal, why this inequality is optimal, was much, much, much more complicated than this. But using this machinery where you need to test your shape against finitely many simplices, it gives a shorter proof. But I guess the more, right, okay, so this translates in the symplectic language to the statement that Virubel conjecture holds for the product of n-dimensional simplex, any simplex, because, the problem is kind of affine, it behaves nicely with respect to affine changes, transformations. So Virubel conjecture holds for any product simplex times anything, Lagrangian product. And this particular case of promotahedron is one of the equality cases. And the natural question is, can we say something about all equality cases? And I'm going to write it under the speculation because it's not written down. Yeah, basically what I claim is that any equality case using the same type of intuition but in a tricky, somewhat tricky way, can be proven that like every equality case is also can be written down more or less in the same way. So every convex fundamental domain of this lattice, which contains n factorial simplices, can be approximated by Voronoi cells of an star with respect to a certain quadratic distance form, which has roughly n squared over 2 parameters. So the family of equality cases has dimension roughly n squared over 2. So here the formula is the same. It's just a different number of hyperplanes passing through the origin, but the formula is the same. And also, these objects seem to be known to people in some kind of discrete geometry who are wondering more generally about, for example, there is a famous conjecture of Voronoi, which says that, also widely open, which says that every polyhedron which you can use to tessellate entire Rn with just translation of this polyhedron, any such polyhedron is a Voronoi cell of some lattice with respect to some positive quadratic form. It's widely open, but this case seems to correspond to some special cases of that conjecture which are known to be true. And just during my last 2 minutes, I'm going to add a little bit of a discussion of this. Okay, so we have this some kind of variable equality for simplex time deformed permutohedron. So one special case of this in dimension 3 we saw in the talk of Jeroen, and it's specifically simplex times something which I prefer calling cat's eye polytope. Sorry, it was not in dimension 3, it was in any dimension. We had this theorem of Jeroen, we heard about it, of Jeroen, Vinicius, and Daniele, that simplex times certain generalized rhombic dodecahedron, which I prefer calling in dimension and cat's eye polytope. You can ask me why after the talk. It's a symplectic ball. So but it's just one distinguished polytope out of this roughly n squared over 2 dimensional family. There is much more. So another point which I briefly touched, that it happens that all those deformed permutohedra tessellate Rn, but the opposite state, the reverse is not true, converse is not true. Not all polytopes tessellating Rn by translations are deformed permutohedra. And I want to finish by briefly mentioning that it's true until dimension 3. In dimension 4, there are several different counterexamples, one of them being the famous 24 cell, which is not even a zonotope. And all my deformed permutohedra are zonotopes, if you know what that means. But there are even zonotopes which can tessellate Rn, but they're not deformed permutohedra. And allegedly, I asked Alexey Garber, and he told me about some mystical K33 graphical zonotope, or zonotope coming from K33 graphical lattice, something like that. So I don't even know how to properly call this object. So allegedly, there are some weird polytopes starting from dimension 4. And these are basic examples which make the Voronoi conjecture very hard. That's it. Thank you.